Yeah, that's it, I guess. Hopefully everything is okay. So this is your equation now. Okay? Can you give me a name for this equation? What is known and what is unknown? What is known and what's unknown? What is given and what is not? What's given, do you think?
The motion?
Exactly, the motion, still this is the motion, right? This is we assume that the motion is function of x times ei omega t. So the part that's function of x, it's your camber kind of thing. If it has just a flat plate, so this would be a constant, not a function of x, that's fine. So this is given, gamma bound is unknown, and look at this. Here we are integrating over eta, okay? I'm integrating over eta. This is a given function of eta. This is a constant, right? Omega bar, it's unknown, but it's a constant. This guy is an unknown, but a constant. You can take it outside of the integral. So almost everything in the right-hand side is known, just subject to a constant. There is some number over there that is not known yet. Okay? So what is this equation? Do you like to give it a name? What's that equation? What's this equation? Come on guys, what's this equation? Do you like to give it a name or it doesn't matter?
Integral equation of...
Exactly, it's integral equation of circulation, right? The right hand side is known, the left hand side is unknown function, and the type of equation is an integral equation. Integral equation for this time the clever analysis by Schwarz. Every time, if you remember the integral equation for circulation, here was gamma wave. That's okay, here we have gamma bound. No, there is a big difference. The integral from -1 to 1 is not from 1 to infinity. So the analysis that the guy did now resulted in this integral equation being the integral here from -1 to 1. It's an integral equation for bound circulation, not wave circulation. Do you have a solution for this kind of equation? If you have something like 1/2 pi integral from -1 to 1, any function of eta divided by zeta minus eta d eta equals some function of zeta. Do you have a solution for this kind of thing? Any solution? Anybody remembers the name of the solution? Exactly, it's Sohngen inversion formula. If f of 1 is 0 or finite, which is our quota condition, then we have the solution right away, Sohngen inversion formula. Say that here is your solution, you're looking for f, here is f as a function of zeta, which is our x normalized by b. So this is -2 over pi square root 1 plus, this one minus for sure, 1 plus zeta integral -1 to 1, the other way around, 1 minus 1 plus, oh, it's the other way around. Okay, times g now, zeta minus zeta dA, right? So in our analogy, what is f, which is unknown? It's the gamma bound. What is g, which is the known? What is the g? What is the g? It's the entire right-hand side is a function of zeta. This is immediately a function of zeta, and this guy is an integral over eta. Do it, okay? If you can, do it. The result will be function of zeta. So the right-hand side is a function of zeta. Just apply it here. You will get missing integrals. That's fine. So I will not go through the details. You can do it yourself, but I will give you the key ingredients. So gamma bound as a function of zeta, here it is. It's -2 over pi, 1 minus zeta, 1 plus zeta, integral -1 to 1, 1 plus eta, 1 minus eta. Here is your stuff, right? I'll do this. So we have here plus I k omega. And we have E negative I k eta, zeta minus eta d eta. But now we need to distinguish actually, these should be not eta anymore, because we reserved the eta for here, we have d eta. So let's call this lambda, lambda, lambda. Doesn't matter, it's a dummy variable of integration. And here we have 1 over zeta minus 8. Yeah, here is the thing, which is very messy. So anyway, the trick here is not that hard. You have an integral and another integral. If there is one that is easier than the other, so please go ahead and do it. And it turns out that the one that is finite is easier. So carry out the integral over eta first, before lambda. So whatever. So the guy managed to find gamma bound as a function of zeta. Everything in the right hand side is known in terms of this distribution, which is known. But there is this guy, right, in the right hand side, correct? The omega, which is the bounds, the total bound circulation. Remember, this guy is gamma over b e I k. So this is the total bound circulation. It's a number. It's a number. So we got the bound circulation. Everything is known in the right hand side except a number that is what? That is the total bound circulation. Do you have a way of getting it? Can you think about it for a minute and give me a trick to? It's not a trick, but it's an obvious way. So this is the distribution. Equals something, but still here there is an unknown. What's this unknown? It's the total bound circulation. What's the total bound circulation? What's that? What's the definition of it? It's the integral of this guy, right? So simply omega is gamma eos ik. So it's eos ik over b times gamma. Here is the definition of gamma. It's the integral of this guy. And you have to multiply by b here because it's non-dimensional. Right? So this guy has omega in it. So this equation has one unknown, large omega. Get omega. Of course, there will be messy integrals, and luckily these guys are very smart, or at least they have tables of integrals. They can use them very well. The tables of integrals give you these integrals in terms of Bessel functions and Haeckel functions. So this is omega. So the problem is solved.
Sir, I have
Yes?
a question here. In this case, if the gamma bound is unknown, the distribution is unknown, and if you want to find out the omega unknown, then how can we integrate the distribution which is already unknown to get the,
What distribution?
like the gamma bound distribution to get the omega, which is also unknown?
No, the distribution as a function of zeta is not unknown. It's known. Everything here is a known function of zeta, but there is a parameter that is unknown, right? This omega is a parameter, is a constant. And there is integral from -1 to 1, of course, because this integral doesn't go away. The integral of 1 plus eta, 1 minus eta, d bar of eta d eta. Okay? So, any questions so far? Like I said, I really see this very straightforward. I mean, ignore the very detailed integrals. Yes, it's heavy and it's not obvious, and you will need mathematical a lot, help of mathematical a lot to get it. But I'm talking about the approach, the bird view. No penetration boundary condition. I have two unknowns, get the relation between these two unknowns through the conservation of circulation. So now I have one equation in one unknown, right? assume harmonic motion because it makes things easier. If before you had two independent variable x and t, now you get immediately rid of t and you just have something in x. Substitute by gamma wake in terms of gamma bound, what we get from the conservation of circulation. So now you have one equation and one unknown. It's an integral equation, which is hard, but luckily now it's written on the bound, not the wake, so we can apply this formula, Sohngen inversion formula. We got the solution. Still, it was in terms of one parameter, but luckily this parameter actually is also related to gamma bound. It's the integral of gamma bound. So just integrate, you get the parameter, and we're done. So from here, actually the gamma quasi-steady is negative 2b times this integral. So this means that gamma divided by gamma quasi-steady is negative 2 over pi ik, and we have e to the ik here, so this is negative ik, h1 plus ih naught. Okay? And remember that k1 of k of ik, so I will just do it here. This is e to the negative ik over ik, k1 of ik plus k naught of ik. So this is the frequency response of this is what I gave you a few lectures ago. I told you we'll derive it later. Here it is. Because Theodorsson didn't give it. Theodorsson got the lift divided by lift quasi-steady, Theodorsson function, but didn't get the transfer function for circulation. And I told you that they are different, and the circulatory lift is not lifted into circulation. Hopefully we'll have some time today to show it in detail. But anyway, here is straightforward from Schwarz work. You can get the transfer function in the frequency domain. Can you tell me what is the transfer function in the Laplace domain? So gamma divided by, so this is gamma bar, this is gamma bar, this is gamma bar. Now there is no bar anymore, because bar means what? Bar means the coefficient of ei omega t. So this is by definition, it's ei omega t type of stuff, it's frequency response. Harmonic motion means frequency response. Now I'm moving from the frequency domain to the Laplace domain. This is general transfer function. So do you like it to be in S or P? Just don't wanna confuse you. Do you like it S? Do you like S for Laplace or P?
S.
Yeah, but just keep in mind that we had S before us time. Okay, I'll do it here. Yes. And just put in your mind that K is omega, right? So this is E negative I omega, right? This is I omega, this is I omega, I omega, I omega. Can you give me the transfer function of S? What you will do?
Replace I omega with S.
Very good. So this is e to the negative S over S, K1 of S plus K naught of S. Immediately we get the transfer function in the Laplace domain. And if you have the transfer function of omega, of the circulation, you can get the transfer function of the gamma over lift, right? Like we did before. Just multiply and divide by in the circulatory. I will not do that because we did it before. Any questions so far? So this is Schwarz, 1940. Very straightforward, very clever, applies, and we got an analytical solution. Remember, to Theodorsson we did not solve the things. We just were lucky enough that the ratio of the integrals meant C of k. But here we solved the integral equation itself. Over there we could not solve the integral equation. Here we solved the integral equation, so we have this guy, we can get the pressure distribution, everything. So anyway, let's summarize now the three approaches. The theoretical modeling of unsteady aerodynamics. reason it doesn't see this line. Wow. Well, that's amazing. Okay, anyway. So at least this is gamma quasi-steady, and at least we'll close this. Anyway, this is too little for Tudorson, that's okay. So Tudorson, 1935, von Karman and Sears. It's the same von Karman that you take the turbulence course that Professor Ulash keep talking about. So it's the same von Karman and Howard, that paper. And he was a professor at Caltech. Sears was a student, PhD student. And we have a street on the von Karman here you can find, right? And this is 1938. Then Schwarz. I mean, there are other efforts, but I think everything else will follow one of these guys. So we will see, when we see the three together, we will know the difference, how they approach things differently. This is 1940. Let's recall together how everybody approached things, and hopefully I will have some time at the end to discuss the unsteady thin airfoil theory and the work of Peters to tell you how circulatory lift is not lifted into circulation. Hopefully we'll do that. So let's remember Tudorson. Tudorson divided the flow into non-circulatory, right? So non-circulatory, there is no circulation. So he has to introduce something that is non-circulatory. I mean singularity. So the singularity he introduced is a source distribution. Whenever you introduce a singularity, it's unknown. How he or we get this guy? What's the condition used? Do you remember? If you have this problem and I tell you this cylinder is moving up and down, please determine the circulation the source distribution. Please determine the source distribution. What condition you will use?
No penetration.
Yep, it's the no penetration boundary condition. So the no penetration is what is Q. We proved that it's 1/2 the radial velocity at any theta. The no penetration is this equality, that the V radial is the V radial due to motion. Is this equality. And because of this unknown, you can immediately get your Q. Okay? Once we get Q, then we have the Bernoulli. And when I say Bernoulli, of course, I mean the unsteady Bernoulli. The Bernoulli gives you the lift non-circulatory as a function of time, which is negative